Hello everyone, my name is Perumal Jagan. I'm elated to welcome you all in this special occasion. We are celebrating Independence Day in India, and I would like to wish my fellow Indians happy Independence Day. Uh, in today's video, let's try some reverse engineering. Already I made a couple of videos explaining a basic CPU architecture and also the assembly instructions. Now I actually found a Try Hack Me room that explains how to perform, how to do a basic reverse engineering. In this video, I'm going to try that, and I'm going to showcase how you can reverse a binary, a Windows binary specifically. And in this video, since we are going to learn the basics of reverse engineering, we are going to use a disassembler. We are going to disassemble a binary, a simple binary, and we will dissect, and we try to assess the functionalities of the binary, right? Without further ado, let's get in. Now you are looking at that room, Try Hack Me, and you see the title, Windows Reversing Intro, Introduction to Reverse Engineering x64, 64-bit Windows software. Now we mostly use 64-bit Windows system, so this is relevant. When you have a skill set of assessing a binary, a 64-bit binary, then it's obviously gonna be very helpful to you when you are witnessing any real world unknown intriguing software. Fine. Now I have solved this challenge a couple of days back. So when I solved this challenge, I posted it on my X platform, X profile, and you see my how I felt when I accomplished it. This room has stuffed a ton of things into my mind. Perhaps I should take a breath and revisit it. And I'm taking this as an opportunity to revisit this, and I'm gonna proceed. Explaining this reverse engineering stuff. As I said, in this challenge, we are going to take a couple of basic binaries, and we're going to reverse it by using IDAFreeware. It's actually a disassembler available for personal use. Freely you can download that. It's a freeware, so with limited features, and I'm going to use that tool, and I'm going to showcase how you can reverse a binary. All right, now let's get into that room overview. If you don't have your machine, maybe you can use Try Hack Me's instance by clicking this, but I have installed IDA on this machine in my Windows VM, so I don't need to start this. This room is part of a series of rooms that will introduce you to reverse engineering software on Windows. This is going to be a fairly short and easy room in which you will be introduced to how higher level concepts look at a lower level. You will also start to get familiar with IDA. We will use the skills learned here to perform more advanced reverse engineering techniques in future rooms. The programs provided in this room are compiled with MSVC. So it's a compiler they are referring. C++ compiler built with Visual Studio, set to release mode for x64. Debug binaries and symbols will not be used to teach with. However, debug symbols will be provided for those who are curious. I'm not positive what is debug symbols are, because I am also a beginner to this. So, but what they are trying to say is they provided the binary along with its source code and the debug symbols. They recommend not using debug symbols as it might crash the machine if the machine doesn't have an internet connectivity. So that's what they're trying to say. If you are using their machine, then they recommend not using the debug symbols. All right. This is done to make everything as realistic as possible. Debug symbols are luxury when reverse engineering and aren't common when dealing with executables. So before we dive in, let me show this and understand. We will have a better understanding on debug symbols. Explanation. Debug symbols explained. A debug symbol is a special maker or label programmers add to their software programs to help them understand and troubleshoot the code. Debug symbols are not human readable, but programmers use debugging tools to interpret them and get meaningful insights. What are symbolic debugger? Allows you to step through the source of, all right. Um, what is debug symbols in iOS? Okay, debug symbol, special kind of symbol that attaches additional information to the symbol table to an object file. So looks like debug symbols are the sources of additional information about a binary. But typically when you witness an unknown file, any malware, potential malware, you don't get the debug symbols. Of course you get just the binary. So with that, you need to reverse and you need to assess what it, you need to infer what sort of behavior it possesses. Fine. Let's get hands-on. So they just gave some guidance how to connect to their machine. So this is not gonna be useful for us, but let's go to the next section. IDA overview. Tool introduction. So they are trying to give some introduction on the tool that we are about to use. In this room, we will be using IDAFreeware, and I have downloaded it and kept it ready. Historically, the downside of IDA has always been its pricing. However, it's actually a paid tool. If you want to use IDA Pro, then you have to pay. It's quite expensive, but there are some pirated versions of IDA available, but those pirated versions are distributed along with some malware, some intriguing files that you don't want to be that you don't want to have in your system. So that's why it's recommended to use IDAFreeware. If you can't afford, if you want to get the extensive functionality, then it is recommended to use the disassemblers like Ghidra, because Ghidra is open source, available to everyone. It could also be used, and the rest of the names you see here denotes a debugger. WinDBG, x64 debugger, or the debuggers. Debuggers are nothing but a tool that you may use to analyze a binary by running it. You can stop that binary execution whenever you need, and you can assess its behavior at every stage of its execution. So that's the use case of any debugger. Fine. My daily drivers are x64 DBG and Ghidra. So this is about the creator. IDA used for this series since it is easy for beginners and results in us only having to use one tool. First, let's discuss the static and dynamic analysis. The static analysis is nothing but without executing the binary, you try to open the binary on a disassembler and assess its code and assess its assembly instruction and try to deduce its behavior. And that's the static analysis. And the dynamic analysis is all about running it on a debugger, and stop at a place you want and try to assess its behavior by just executing it in a debugger. So that's the dynamic analysis process. There are three main functionalities that our tools will provide. Those are debugging, disassembling, and decompiling. These three terms might look similar, but they have subtle difference. Debugging is, as I said, it's all about running a binary in a controlled environment, running a software in a controlled environment. Disassembling is something assessing without executing it, just gonna read how its assembly look like on the disk. And decompiling is all about trying to reproduce the high level source code, human friendly source code. But in any disassembler you take, the decompiling option, the decompiling feature is not reliable at all. It might be wrong. So you cannot completely trust the decompiler that are associated with a disassembler. Disassemblers will translate the program into bytes, disk, or in memory into assembly code equivalent, present it in an informative way. So in disassemblers, you could see, as they said, the program from its bytes on the disk. So it will show how it would look on the disk. Decompilers are similar to disassembler, except instead of giving us the assembly, it attempts to recreate the code. As I said, it's trying to recreate the source code, the user-friendly code, high-level language. And the debuggers alongside disassemblers and decompiler will allow us to place breakpoints within the program. As I said, when you are executing a binary, a program, you can control it. You can stop that execution whenever you want and whatever the place you want, and you can stop it and you can try to assess its property, how it behaves, and that's all about the debuggers. I'm just mentioning, I'm just giving the theories about the disassemblers, debuggers, and decompilers. IDA is actually an extensive tool. I'll only, okay, he's going to show only the limited usage as it's a beginner friendly room. To load a program into IDA, you can start IDA, then follow. So, okay, this is not a big deal. Maybe I'll show it when I'm trying to load a binary on IDA. Fine. Debug symbols. What are debug symbols? Debug symbols are extremely helpful and you should use them when you can. Unfortunately, you will usually only have debug symbols for common libraries and rarely for the executable of interest. Well, that's what I just mentioned. When you are witnessing or up against any unknown binary or a malware, you will just have a binary. You don't have any other information. So in that case, you must rely on the binary. You shouldn't rely on a debug symbol always, because it's not always gonna be with you. Fine. In addition to that, most reversing tools download symbols for common libraries. If you don't have an internet connection, you won't get them. Okay, this is an additional point. So the reversing tools download symbols for common libraries. So based on the libraries used on the binary, it's gonna download, the disassembler gonna download debug symbols. For that, you need to have an internet connectivity. All right, that's a note to remember. And that's why they are not, they're asking us to not use a debug symbol on their machine. But we are going to use our machine, our IDA. So if possible, we will try to use debug symbols given to us. All right, code views. Two primary views, list view and graph view. You can see this graph view. You can get this graph view when you are using IDA. It's an excellent functionality. You can see the set of assembly instructions, a block of assembly instructions, and from one block to another block, and you can see the links, green link and red link. So when the condition is true, a condition passes, it chooses the green link. When it fails, it chooses the red link. Like that, it works. So it's gonna helpful to trace the flow of the program. So that's very important. If you're using IDA, you will get this feature. As you can see in the graph view, the allow represent destination of jump instruction. This is incredibly useful and massive time saver. You can see this is the list view. When you see the same program in the list view, it might be confusing. It might be creating some confusion. But when you see the same in the graph view, it might be little clear, a little better. All right. Fine. You may find it helpful to enable auto comment. So here is an option to enable comment in a disassembler, IDAFreeware. So for that, you need to go and choose this option, auto comments. So the comments obviously gonna help to understand the assembly instruction. You need to have an internet access to be able to decompile code with IDAFreeware, so it will not work in the provided VM. Well, when I was trying this challenge, I used the TryHackMe's VM, so I tried to decompile it, but unfortunately, it didn't work since it didn't have the internet connectivity. But now we are going to try it in our machine, and I have the internet connectivity, so I can try to generate its decompiled code. Fine. The next section is import and exports. Actually, they are trying to dissect the IDA tool and the sections of IDA tool. The next section is imports and exports. So if you see these imports and exports, it's going to list the functions that are associated with the specific program. For example, if it is an executable, obviously it's gonna if it is dynamically linked, it's gonna rely on some libraries. So it will get some functionalities from the library. So obviously some functions will be on the import table. If it is a DLL file, so it is going to be used by the other executables, other programs. So obviously you will see some functions on the exports table. So these are the two tables where you can witness the functions that are associated with the binary. All right, fine. And the next one is functions. You can see the function window and show the identified functions of the current program. Well, I'll show it once I open a binary on IDA. You could see the list of functions present in that program. So that's what they're trying to say. And sometimes you may see the function name quite different, like this, in this format. If you see a function name in this format, then you can assume that function was not recognized by the function that was not recognized by the disassembler, and it gave the name based on its memory address. So whatever the number you are seeing here after the underscore is actually the memory address of the specific function. Okay, just an information for you. And other sub view, you can enable other sort of views like string view. In string view, you can view the human readable strings that are present on the binary. Sometimes when you look at the strings, it will give you an insight what this binary is exactly doing, and what are all the libraries. Sometimes it may expose the libraries that are used. So it will give an insight. It will give us an insight what it actually does. Right? That's fine. And let's go to the further learning. So far we haven't asked any question, and now the real challenge begins, the explanation. This is also just a theory part. Prologue and epilogue. I already explained this prologue and epilogue part in my previous processor explanation. When we were trying to learn the processor architecture, I actually explained this prologue and epilogue. And also when I was explaining the assembly instructions, we have learned what is prologue and epilogue. It's actually a set of assembly instructions that are executed before and after the function call. Okay, so that is simple, as simple as that. Now, since we are handling the 64-bit binaries, the 64-bit architecture, we would see the registers that begins with the letter R, because it is the symbolic notation. It's the symbolic representation for 64-bit architecture. If it is 32-bit, then you would see E instead R. Okay, that's fine. We don't need to read more and confuse ourselves. So let's get into the next one, and this is where the analysis begins. Let's see this. So we are given some task files. So let's download these task files first. Yeah, it's being downloaded. So once it's downloaded, I'm gonna go to that path. Yeah, here it is, and I'll change it to my work directory. Try hack me Windows reversing intro. Here I'm going to extract it. Perfect. Now it extracted, and I'll see the list of files within this. Okay, open in terminal. All right, now you can see this, right? Fine. You see the folder debug symbols. So we were given the debug symbols as well, and we have the source code, and there is a binary, HelloWorld.exe and Loop.exe. So we have two binaries, and let's get into that source code directory and see how many source code we do have. So the respective source codes for those two binaries, hello world and loop. All right, fine. Let's get into that and try to read this. Readme.txt. To be as realistic as possible, don't use debug symbols or source code unless you need assistance or are exploring on your own. Fine. I'm not going to use debug symbols for now. Maybe when we struggle, or once we have done assessing the binary, then we will try to use the debug symbols. Okay, fine. But first of all, if it is not a malware, if it is a benign sample, then you can feel free to execute that sample and observe its behavior before you start the reverse engineering. If it is malware, that may not be applicable. You directly need to load it on a disassembler and try to assess its assembly instructions. Fine, just an information. Since we are handling the benign samples, so I have no issues in executing these two hello world and loop binaries. So let's see. But before that, let's see the source code of it. I'm going to go to that source code directory once again, and let me open this. I'll open it in Sublime Text. All right. I'll go here and open a folder. Maybe yeah, open folder. Here, if I go to documents, try hack me, Windows reversing intro, source code. Yeah, this is the folder I want to open, and I see the couple of source code. As I said, we are handling a simple program, and you see it's a C++ IO stream, a basic library to handle the input and output. Main function is called, and you see the function definition. Printf, they are calling a printf function to print some strings on the terminal, and they are mentioning that it's string, and in new line they are printing this specific string. All right, and then the next one, standard cout, std cout. This is actually another method to print text on the terminal, and you see they are getting this hello with standard out string as an input to this specific maybe function or method. I'm not a C++ guy, so this is, they are just getting this into this specific print function, standard out function. Fine. And finally it's returning 0, so it's gonna print some text, a simple program. But when you open its binary on a disassembler, you will see bunch of stuff, enormous stuff, because the the compiler actually does bunch of stuffs to convert it into a machine readable file. Okay, so let's read through that. But before that, let's see this loop.cpp as well. Let's see what it does. So it gets two libraries, IOStream and string, and in the main function there is a variable defined, so its value is 0, and standard string input, it's getting some string input, but before it's getting that string input, it's printing string colon, and it is asking us to enter some string, I suppose, and it's entering into the for loop. So once we entered the string, it calculates the length of the string, and it defines that length as a limit to this loop. So it iterates from 0 to that length of the string, or lesser than one value of that length of the string, and it actually iterates between that values. And what happens here, it's getting the input, right? So it's taking one letter at a time, and let's see, it's getting one string, one character from that string at a time, and it compares it with this. So what it does, it's try to check whether it is alphabet small letter, alphabet A or greater than A, which means it could be A, or in ABCD any other letter, and it is actually checking another limit. Here it's trying to ensure the letter is less than or equal to Z, so which is nothing but what this line does, it try to make sure the string that we enter contain only the alphabets A to Z, that also the lowercase, and it tried to count that how many characters we entered. So it tried to count that, and once it counts that, it prints how many characters it has. Well, that's what it does. Okay, simple, fine. Now I'm not going to close this. Let me go to that binary and execute it and confirm its behavior. Dot // to call the binary. Now I am executing hello world. When I executed, you see only 2 lines got printed as per the source code, hello from printf and hello with standard out. Fine. And let me execute another one, Loop.exe. And here it is asking us to enter some string. So I will give my name, Perumal Jagan, and it's counting the number of characters we entered. It is 12, counted 12 lowercase characters. Fine. Now what if I enter some uppercase and give some space like this? Let's see what happens. Counted 6 lowercase letters. So what it is doing, it is ignoring the uppercase letters. It is just picking the lowercase letters and it's counting. And that also, here it counted only 6 lowercase letters because it ignored this P, and from here it's counting. There are 6 lowercase characters. When there is a space, it breaks the program. So that's the behavior. That's an expected behavior. When the letter is not between A to Z, it actually comes out of the loop and it is printing the result. All right, that's expected. What if I use some special characters? I think the behavior is same. Anything that you use apart from small lowercase a b, a to d, you will get the same result. But here it's quite different. Look at this. It ignored the space, but it counted 10 lowercase characters. So it counted this underscore. It treated this underscore similar to this capital character, the uppercase character. Now it counted 6 lowercase from here and 4 lowercase from here. Now it's printing 10 lowercase letters. All right. Now we deduced the behavior of this binary. Actually, we found apparently the behavior of these binaries. Now we know it. Let's learn the same through the reverse engineering. I'll go and open the IDAFreeware. And here I'm trying to load the new file. Documents, try hack me, Windows reversing intro, and I'm loading this HelloWorld.exe. All right. Fine. This input file was linked with debug information, and the symbol file name is, so it is also asking us to link it with the debug symbol. I think it is asking, I mean, the disassembler is itself gonna retrieve the debug symbols for us. But can we do that now? I'm gonna give no just for now. I'm simply loading the binary. I'm not loading the debug symbol for now. Maybe once we have done the assessment, we will try to load it at the end. Okay. Let's see this. Now you see the list of functions here, and here is the table. Function name. It contains bunch of functions. And here is the main function, and you see the other functions, which are suffixed by its address. And you see the bunch of functions that are involved in this. When the program compiled, it added all this compilation stuff. These are all the compilation elements which are essential for a program to get executed. Fine. Now we have opened it. Let's follow the guide and read through this. Getting started. Let's take a look at the sample that calls a function. For this task, HelloWorld.exe, it's usually a good idea to run the program before doing any reverse engineering. So go ahead and do that. So we have just did that. We are going to start the main function, find it in the function list, and we could see that here. I hope you could see this properly. Maybe I'll try to enlarge this. Let's see how to do it. 16 like this. Yeah. Now it's better. Okay. Options, general, comment indentation, space, analysis, miscellaneous, disassembly, cross references, right margin, disassembly, browser, number of lines per lines. Okay. Graph. Okay. I'm just trying to enlarge this function pane as well. That's fine, no issues. We will try to read through this. We are going to start the main function and find it in the function list, and we could see that I have chosen, and now we are seeing the main function, and you could see the strings here. Before we start this, let me load the comments here. To see the comment, we need to go to options, general, and disassembly, and here you see an option, auto comments. So if you apply this, and you could see some strings got added at the end of every assembly instruction. So this is the comment. It's gonna say what the specific assembly instruction is doing. So it is gonna help us to understand it better. Find it in the function list. IDA doesn't navigate it automatically. The main function look like something like this. Okay, we got that. And notice sub RSP28H at the top. And I could see that here integer subtraction. So it is actually a subtraction instruction. It is subtracting the value, the hexadecimal value of 28 from the stack pointer. So RSP is representing the stack pointer. It's a register to represent the stack, top of the stack. All right. For this function, the entire that's the entire Prologue. It's setting up the function by moving the stack pointer by creating the new stack frame area. Well, they're trying to say this specific one instruction is the Prologue for this entire program, because it is setting up the new stack frame for us. So it is doing some operation on this stack initially. So probably it's the Prologue. Okay. And let's see the printf. For now, we will focus on the first function call with main. Let's see the source code here. And here we could see in the main function, we've seen two function calls. One is printf and another one is standard cout. First, let's see this printf. It doesn't resolve that this is the printf. So instead, you can identify it such based on the parameters passed and what it does when program runs. Well, what they are trying to say here, you don't see any word like printf here. We are just identifying it as a printf function based on the things that we are passing into that, maybe the string, right? So that's what they are saying. Let's see. You can identify it as such based on the parameters passed and what it does when the program runs. IDA shows two strings loaded into first two parameters of the function calls. Okay. The first parameter passed via RCX, which is nothing but the %s, and second parameter in RDX, which is nothing but the string. So what they are trying to say here in this function, they are passing two parameters. The first one is the type of data that we are passing. It's a string data. And the second one is the data itself we are passing. So there are two strings within this function. So that's what they are trying to say here. The first string is getting passed into RCX, while the second string is getting passed into RDX. So that's what they are trying to say. Let's see, is it the same case? And you see the first one, RCX. So it is actually passing the format which is nothing but the %s. When I keep my cursor on this, you could see the percentage yes here. So what is happening exactly? So it is trying to refer the string, the type of data, the first string that is passed into the program, %s \n. So I can just click this and go to the main function again. All right. Now the second one is RDX. Something is loaded into this RDX. What it is, which is nothing but hello with printf. When I keep my cursor on this, you could see the string clearly in the green. Hello with printf. So when I double click this, I've been shifted to that specific string. You could see hello with printf, and when I just click this, it will again bring me back to the main function. So these are the two stuffs get loaded into each RCX and RDX registers. And next, once it is loaded, it is calling something, but let's try to read that. Immediately after two parameter in the call, the IDA you can rename whatever you want by right clicking and going to rename by selecting the function and pressing N. Rename the variable. Okay, here they are trying to give us an explanation about the renaming. Let's see. I'm gonna go to this main function. Here I can right click and I can rename. Here they already named it as format, so I just leave it as it is, but you can rename any string that you want, or any parameter within the disassembler you want, just for the sake of understanding. This one, hello with printf, may I rename it like that? Hello with printf, like this. Okay, yeah, I named it like this. Fine, now it's better. I'm gonna go and read through the next stuff. That's it for the call printf. The first parameter in the format string and the second is hello string. Printf makes the magic happen. Feel free to look the printf more if you would like. Let's see what it does here. I click this here. Okay, so this is the graph view. That's all right. I'll come back. Let's see this. All right. I think this is the printf call. So this is the system call, I suppose. Integer subtraction, load effective address, indirect call near procedure. Do I see any function call, a system call here? Yes, these are all the directors. System call, integer subtraction. Okay, I go to main function. So let me read through this. Std cout. Now let's look at the second function call, which is to std cout. We can identify its std cout without using the string printed on the console, because we can see things related to cout, basic ostream, and char traits. Let's see this content. We see basic ostream, char traits, and cout here. So without seeing this comment, we can identify this line is related to the second line of printing some text with standard cout. Let's see, that's what they're trying to say. You may notice the names of the functions are quite odd as displayed in IDA. We will discuss this in DLL section. In short, the names are mangled for function overloading. You see the list of function names here. As I said, these are suffixed with its address, because they call it as mangling. They call it as mangling. Mangling is nothing but changing the name from its original name to something else. For now, look past the name mangling. With that said, you may not familiar with those functions. Okay, now we see three functions here. Cout, and you see the cout's definition. Let me go to the main function. Cout, basic ostream, char trait. They are trying to explain its function here. Basic stream. C++ template for output streams. Okay, the basic O stream is actually a function used to represent the output streams. Can I say like that? Explain. How about, it's a class template. Basic OStream is actually a class template, provides support for high level output operations on character streams, so it's relevant. And what about char traits? Let me copy this, char traits, and explain. Char trait, it is also a class, trait class template that abstract basic character and string operations for given character type. So again, this is a relevant one. I'm gonna go and check this cout. Let's see what is cout. Cout in C++ explain. The instance of OStream class. So C++ cout is nothing but an instance of OStream class. It is used to produce output on standard output device, which is usually a display screen. So this is responsible for this line is responsible for displaying the content on the screen. So while reversing, we can try to Google the unknown stuffs and we can understand it better. All right, let me go to the next one. Sends the text to the console, provides some abstraction from the basic character to string type. All right, now to address the elephant in the room, where is the string that is supposed to be printed? Let's find out. To go to the string, open subview and strings. Fine, let me go here, view, open subview, and string. When I click this strings, you see there is a string view got added here. So now we are viewing the string and you see the list of strings involved in this. Hello world with printf, hello world with the stdout. So these are the two strings that are present in this binary, which is at least relevant to us, since though there are a bunch of other strings added by the compiler. Fine, I'm getting back to IDAFreeware, and here then look at the string in the list, and you can use Control F to search, double click the string list, and will bring you to the string where you can see all the reference to the string. Okay, I'll go to the string, I double click this, and I see where the string is referenced to. Again, I'm going to string, I'm clicking this standard out and double clicking it, and it is again bringing us to the place where it got referenced. Okay, and once I click this, it's gonna bring me to the main function. Now you see the graph view here. Let me go and search through this. Okay, I'll click this main now. The string only has one reference. To double click it, it will bring you to the location of the string where it is in a very large function. Let's see that. I'm gonna go to the string and let me press this, double press this cout, and you see it is giving some details to us. I'm clicking this one, and now it is bringing to the specific function where it is used, and you see the graph, the bunch of functions, the bunch of assembly instructions that are present in this simple program. Now we are here. You see this one shows how this cout works. Char traits, excuse me, strings, standard out, going here, yeah, and here you see its reference, basic stream, char traits, SPUTN. This is something related to that displaying the contents on the console. Fine, I'll go to this and read through this further. And here it is, hello with standard out. Okay, yeah, and now you see the hello with standard out, the string that is getting loaded into RDX register. Yeah. Fine. Let's see. The string very clearly not where we would have expected it to be. We can see SPUTN, that's what I just mentioned, which long story short means we are dealing with the character streams. So this is actually used to denote some character streams. So what is this massive function and what it is doing? If you go to the top of the function, in the listing view, you can see what references it. Sure, main references this function. So what is going on here? So let me go to the top of this function. Maybe I could scroll like this. I'm not seeing the main function here. Here I'm seeing that char straight. Okay. Where it's referencing the main function. Let me see this. Scal is 1050. Okay, now look at this. Now we are in a main function. When I double click this, I was just shifted to this function definition, the printf function definition. So this is the block that is doing some printf stuff, and you see here some system calls related to printf. And you see it's calling some API. Imports from API, MS, Windows, CRT Studio, some from DLL. So it is doing some printf stuff. I'm going to the same main function, and now you see this call procedure 1400010b0. This is the address of this function. So I'm double clicking it, and you see this. So this is that function. So let's see this function definition. So in this function definition only, we found this specific cout printing. Okay, that is fine. That makes sense now. Let's see what is inlining. One compiler linker optimization that makes noticeable changes to the code inlining. When a function gets inlined, it's essentially pasted where the call would be instead of making the call. Okay, I don't understand this, but let's read through this. Without function inlining, in function, if there is no function inlining, what happens here? There is a main function. In the main function, there is a function call, and they are defining the results, and they are putting the results in this integer, and then they are calling another function add, and here is that function definition. They are adding the value of 5 with the value x, and they are dropping the results in this res. So the main function has the function call, and the function is defined separately. So if there is no inline, the function is defined separately. When there is a function inline, the function is defined within this main function itself. So let's see, there is a random integer. X will be the random integer. That's the function. So it's get a random integer, and then once it gets the random integer, it is just simply adding it with the number 5 and dropping the results here. So it saves the code. All right, and also the it's not defining any function externally. What is happening with our string HelloWorld.exe is similar. Instead of the string being passed as a parameters to stdout, it's directly referenced to stdout. You may think that this would cause problems, because if standard cout is called to print different string, you would be correct. This would cause problems for further calls to standard cout. As it turns out, cout is called more than once. You will not see this optimization used. Instead, you will see it used as similar to how printf is used. Okay, what they're trying to say here. they are comparing this code block with this std out and printf. In printf, to print this specific string, we have called a separate function printf. Okay, but in standard out, we are passing the string within the standard out, so it is not it is handling like all the elements within one function. It is not calling another function. So that's what they're trying to say. That's what I deduce from this para. All right, I encourage you to write a program to play around to develop the deep understanding. Well, that's we are going to do. Maybe while we are assessing further samples, we will get a clear understanding of this inlining and function with inlining and without inlining. All right, let's see. In the HelloWorld.exe sample, which instruction sets up the first parameter for the call printf? Provide a full instruction in IDA. Okay, I go to this main function, and here in the main function, if you see the first parameter, this one, and this is only setting this %yes, and also the new line character. What is this? Is it a new line character? 0AH. Okay, but anyhow, this is the specific instruction that is actually setting the first parameter or the first argument. So that's the answer. And we are going to the next one, loop sample. So which is little difficult from the hello world sample. In hello world sample, we mainly focused on the difference between printf and std out. But here in loop sample, there are a lot of things happening. When we are passing an alphabet, it is just trying to filter out the lowercase alphabets, and it's counting the number of lower digits exist. If there is a space, it breaks the function. If there is no character, that means. All right, now let's see. Download the task files. We have already downloaded that. Let me go and exit this. Maybe I'll use a new instance. Here I load a new assembly, a new binary, Loop.exe. Okay, no, I'm not loading the debug symbol. Fine, I'll close this HelloWorld.exe. And here the Loop.exe, let's see what is exactly happening. So whenever you start a disassembling or reverse engineering, start with the main function if it exists. Now we are in a main function, that's fine. And you see the main function itself got bunch of code blocks. Let's assess this source code, Loop.exe. But before that, why don't we try and generate that decompiling? Try to decompile this code. So let's do that. Maybe where is that option to decompile? I think it is in that IDA overview. Yeah, view open subviews, generate pseudocode. Okay, I'm gonna go and choose this whole stuff. Maybe can I do it like that, or how can I go and do that? View open subviews, or view open subviews, generate pseudocode. Okay, view open subview, generate pseudocode. Okay, yeah, it's decompiling. And look at this. Now it decompiled. It is showing the pseudocode of that specific assembly. And you see this, it is getting some, it did some decompiling stuff, and you see the bunch of unknown stuff. While decompiling, it just substituted it with some standard characters that we don't understand, that is irrelevant. but still they are representing it in this way. So it might be a little difficult to understand. It is not a complete decompilation. You don't get the exact source code, the real original source code. It is impossible. Whenever you are trying to reversing it from the machine language, you will get a decompiled code, something look like this. It will look like this. Okay, that's obvious. Okay, v3 OLL block 0 v16 v17 cout string. Wow, I see bunch of stuffs here. Yeah, see this pseudocode std cout string. It is printing the string and it is getting the input from us. So block means array, I guess. You see, it's actually an array to get the input from us, from the user. And you see the subroutine for that. And its decompilation given here. So what it does, it is getting the input from us. So here is that standard basic I stream to get the input from the user. You see the basic I stream, char traits. So these are all the classes related to the character and string handling, input output stuff in C++. So we just witnessed it. All right, I'm gonna go to this pseudocode again, like this, or to the main function pseudocode. Here scene, I'm getting stuff, and it is actually getting into the for loop. And look at this, the for loop similar to the source code. Size, it is currently 0, but here v16 is nothing but the size of the string we enter, right? Yeah, v5 lesser than v16, and this one input dot length. So it's calculate the length of the input, and that is actually the variable v16 0ll. Okay, and x is nothing but the iteration, the first character or the character that it iterates. That character is v5. All right, and it is actually extending that x++. And what it does, look at this character. What is 0x10? When you convert it into hash key, what you will get? When you convert it into hash key, you will get a, I guess, maybe. Let's see. Hex to ASCII converter. Going to rapid tables, 0x10. What about converting it? It's question mark. Okay, that's okay. Here it is. So I think this is what I supposed to check. 97. Let's see what is 97. I think it is small letter A. No. 122 maybe. Without 0x. Question mark. 97. ASCII table. Okay, I think we are in decimal, right? We are having a decimal value, not a hex value. Decimal to ASCII. So this is where we get that. Where is decimal? 97, and you see 97 is small letter A, and if you see 122, you will see small letter Z. So it makes sense now. So it's trying to get the letters that are greater than 97. I mean the decimal value that are greater than 97, and the decimal value that is lesser than or equal to 122, which means in ASCII it is equivalent to A to Z. So this is what happening in the computer. In keyboard, if you see, when you are entering A, it is actually giving the value that is equivalent to A. It is converting it into binary, from ASCII to binary, and it gives it as an instruction to CPU. So that's what it's actually happening in the background. Fine, I think we have a picture right now. So what it exactly does, so when you decompile this, it is giving us some idea what is exactly happening. So once it counted, it prints that here in v4, and also it is actually printing us that lowercase characters. So simple. Fine, enough doing this pseudocode. Let's get into this assembly instruction. Let's see. We came a long way. We came away. Let's see this one. Initial analysis, reversing our first loop. Okay. Now, before we throw it into IDE, it always should, after running the purpose. Okay. Now I go to this view, not view, yeah, view or options, general, auto comments. So I enable the comments. Fine. Now we good to go. Okay. Go ahead and start the loop and go to the main. You notice it's quite large. Yes, it is. And I see bunch of assembly blocks in this main function itself. Yeah. Now I would encourage you to go to graph view. Okay, we are actually in graph view. There is another interesting stuff. If you press the space bar, it will just bring us to our line view. But when you press space again, it will bring us to the graph view. So I would recommend checking it with graph view. All right, initial analysis. To start, let me introduce you to the best skill to developer. To start, let me introduce you to the best skill to develop as a reverse engineer. So let's see what it is. It's being able to skim over the unimportant stuff. Otherwise, you will waste your time, because what they are trying to say, you need to know where to skip, where not to skip. That's very important. That's an important skill set to have as a reverse engineer. All right. In a graph view, you can see a big box at the top. Yeah, I could see the big box at the top. Looking at it, and you see the graph view here. I'm just hovering my cursor, and it is just showing the respective or that particular block of assembly instruction. The first block is very huge. That's what they're trying to say. Okay, I can maybe enlarge this, or maybe I can, how I can minimize it. Can I close this first? Yeah, okay, I got this back. Okay, we can see a big box at the top. Looking at, we can see that it most importantly just prints stuff, and we can skip through, just make sure nothing is important. Let's see what is happening here. Load effective address. So it's getting some string from us. So nothing important. As I said, I mean, as they said, it is just trying to print something. Nothing important here in this block. But when I just go here and see this block, that's what they are right now referring. Looking towards the bottom of the big box, which I refer the loop initialization of the part of the code. Here we see some interesting stuff. Let's see. And if you see this one, it is just moving a block. A block is nothing but an array, an empty array. It is moving an empty array into this RDI, destination index, and it is moving two variables, where 28 and let me go back. Where is the button to go back? Here. Yeah, okay, here I see where 20 and where 28. So what it does, let's see. Okay, the reason why it is interesting is for two main reasons. First, it doesn't appear to be printing anything like previous lines were. Yes, it's not printing anything. Second, the loop, that there is a loop following it, which can quickly identify because of the arrows provided in the graph view. and let's see what happens here. And I'm seeing a green arrow and a red arrow. So I'll just scroll like this, and here I'm seeing a character A. When I come to this green arrow, I see it is trying to print the result counted, and it is trying to print the number of lowercase characters here, right? So I'm just going here and see here it is calling the letter A and letter Z. It's loading it, it's trying to compare. All right. So that's what they're trying to say. So here it's performing the loop operation. It's getting A and Z. In our source code, we could see the A and Z are part of for loop and its operation. So before starting this loop, there is some initialization, maybe some iteration. In loop, when the iteration is starting, it starts with value 0, the index value 0. So I think that's what they are trying to refer here. Let's start our analysis by taking a look at MOV RSI, this one, 58H var 20. Since it seems to be the start of the difference, important, don't forget about the code we just skimmed over. All right. Looking at the move to RSI, RDI, and RDX. So this one, RSI, RDI, RDX. We don't get much since the data is uninitialized. Notice that test RDX and RDX as it can reveal little extra. And look at the next instruction. So it is actually comparing the values present in RDX with itself, and when the value is when the values are equal, since it is comparing to a same register, the result of this test will set the 0 flag register to 1, I guess. So let's see. Testing a register against itself will test if the register is 0. In this case, the RDX is 0 and it jumps past the loop because JZ short LOC. Okay, now the next line, what is happening here? So it is testing some condition here. If the condition is true, if the condition is passes, it is moving to this location. So what is this location? It is just coming here. It is trying to print the results, but if the condition is false, then it is getting into this block, and you could see the red arrow, green arrow. Green arrow means if condition succeeds, it moves to that place. Red arrow means if this is not succeed, this is going to this specific assembly block. So that's what happening here. Yeah, let's move like this. Based on this, we know that RDX shouldn't be 0. Now we know we want to get into this loop because we need to make sure the letters we are entered is as a small letters, the lowercase. For that, it has to enter into this block. It shouldn't go to the end, so that we know the RDX should not become 0. It should, maybe can I say like that? Based on this, we should know that the RDX shouldn't be 0. Since it appears to fail or skip the loop. Since we are iterating over input, we can guess RDX is most likely the length of the string. So this RDX is what? It is actually holding the length of the string. Okay, but it could also be checking if buffer is empty. Fine. So we actually allocated a buffer to get an input from us. We are going to give some lowercase string. For that, it allocated some buffer, and you could see the buffer block here. This RDX could also be that, right? But one of the nice thing about IDA is it can determine the data is buffer or just a normal data type such as an integer. And here is the differentiation. It clearly differentiating. If you see the word block, then it is actually a buffer. If you see a variable here, which is nothing but a value, which is not a buffer, it's a value. So it is clearly differentiating what is buffer and what is value. Now we clearly say the RDS is actually the length of the string. Yeah, fine, that's what they're trying to say here. And let's analyze the loop here. We go to this specific block. The first thing I'll do is I go to the end of the loop and identify the register is being used as a counter and the end of the loop. The key to finding the counter is identifying the register which gets incremented or decremented. In the end case of the loop can be identified as comparison of the counter. Let's try and see that. I'm going to this place and look at this one, this block. What is happening here? It is actually incrementing the C block, the C register, the counter register. I think it is counting the loop iteration. Now what happens? It is comparing the length of the string with the loop iteration. If it is equal, which means if the complete iteration of every character of the string is done, then it is moving to the specific stuff. It's trying to check whether yeah, I think it is trying to check whether it's a lowercase or not. So I think that's what they're trying to say here. At the bottom you can see RCX being incremented then compared to RDX. In other words, the counter is compared to what we assume is the length of the string. Now we know RCX is the counter and the condition between RCX and RDX is the end condition. This also solidifies that RDX is the length of the string. So just to confirm that this RDX is nothing but the length of the string, they just referred this specific block where it is. This one. Since it is comparing the RDX with RCX, RCX is allegedly the counter register, which is counting the iterations of the loop. Okay. At the bottom you can see RCX being incremented. Okay, that's what they are saying. Loop block 1. So let's get into this one. So what it does, it is getting some value, some buffer. So whatever the character we are entering in the buffer, it is loading it into RAX, right? So let's see what it does. Once again, you must try to understand the multiple instruction together. It's a load effective address, which means it is loading the address present in this RSP into this register. Okay, we see the address of the buffer. Yeah, it is loading the address, the buffer address into RAX. And RAX is how the string will be referenced in the loop. Now, what is the weird RSA comparison of CMO VNB? Instruction is actually a conditional move. C move is nothing but conditional move. This is saying move RBX into RAX if RSA is not less than 0 into 10. What it is? Decimal value of 10. Is it a space? No. Let me check this. Reset. Like this. 10. What it is? It's a space, right? It's a space. Okay. This is saying move RBX into RAX. Move RBX into RAX if not less than 10. So this is the 10 hexadecimal value. So it's comparing. So when it compares, the RSA value must be greater than this 10 value. Okay. So it is moving this stuff. RDA into RAX if this condition satisfies. Okay, these two specific assembly instructions. Okay, let's find out what RDI is. Okay, this one we need to understand. What is RDI? The initialization block, the big one at the bottom. We see the string buffer moved to RDI. Okay, so the first line, if you go to the first line, the top of the stuff, and here you could see the RDI. The string buffer is getting moved into RDI. So that's what they are referring right now. The RDI is moved into RAX. Okay. Okay. since RDI is 8 bytes, okay, the first 8 bytes of the buffer are moved into RDI. Note that unlike RAX, RDI doesn't contain the address of the buffer. The RDI doesn't contain the address of the buffer. RAX was given to address before LEA instruction, whereas RDI given to first 8 bytes of data within the buffer because MOV instruction. Okay, there is a subtle difference between the MOV instruction and LEA instruction. Let's see that. This one is actually the MOV instruction. So it is moving the content of RDI into RAX. But whereas when we go to the first block, we could see, yeah, this one is actually the MOV instruction. It is moving the first 8 byte of data which is present in this block into RDI. But when we go here and see LEA, look at this one. It is actually moving the address of that specific buffer into RAX. Okay, now this RAX will contain the address of the buffer, and now when the condition satisfies, it is just going to, the RDI will have the data, the specific data that we enter, and once this C move, the conditional move is executed, the content that user entered will get moved into the buffer. Can I say like that? Yeah, the A register. So which is something like that. Now RSI, we see the bottom of the initialization. RSI is set to unknown value. Keep looking at find the modifies the variable. You will see towards the middle of the block. It is initialized to 0F unless RSI are modified elsewhere. C move will never occur since ORF is below 0.10. Okay. So it's a bit confusing here, but I'm just trying to read this and understand. Now for RSI, we can see bottom of the initialization block that RSI is set to unknown value. Okay. So it's set to unknown value. Keep looking to what modifies that variable, and you will set towards the middle of the first block. Okay, you will see towards the middle of the first block that it initialized to 0F. Can we see that? To the middle of the first block. Look at this. It's initialized 0F into the specific RSP. Yeah, correct. This block only they are referring. Unless RSI or RSP 58 var 20 are modified, okay, the C move, the conditional move will never occur since 0F is below 0.10. So let's see what is the value of 0F. 0F is actually 15. 10 is actually 16. Let's read through this. 0F is below 0.10. Yeah, so 0.10 is 16. The decimal value is 16. But if it is F, then its value is just 15. Okay. So what they're trying to say here is, let me go to that reversing stuff. Here it will not get executed. The conditional move will not get executed because when it get compared, this 10 value is actually greater than this RSI value, because in RSI it contains the F value. You see it here. The F is loaded here. Yeah, the F is loaded. RSP 58 var 20 contains F. So that F is loaded into RSI. So this condition, this comparison will never occur. It will give the negative value. So obviously this conditional move will not exist. Will not go. I mean, will not happen. So since it is not happening, the comparison will occur. So what will happen? Okay, fine. I think now I got the stuff. If this C move, the conditional move succeed, if this comparison succeed, it will move to conditional move. If it moves to conditional move, then I think this green line, it follows the green line and it comes to this block and it increments the counter. But here, since it got failed, it is coming to this comparison. Here it is taking the value 61s, hexadecimal 61, which is nothing but the value A, and it is getting compared to the RAX plus RCX combined. I think it's a memory pointer. It is pointing to the location of RAX and RCX combined. Okay, let's see. So what exactly all this doing? Since it doesn't appear to be related to the loop, we will come back to this. Okay. Now next, there is a comparison between RAX, RCX and 61. Then jump if it is less than. Okay. This is getting an offset in the string with the distance that being loop counter. RAX and RCX is the same as string index or RAX RCX in a high level language. Okay. RAX RCX is nothing but it is reading a character from the string and it is comparing that specific character from the string with this A. So that's what happening. Now let's break down more understandable way. It will compare the current character in the string that being iterated over against the character A. And the current character is less than A, it will skip to the final block and the loop, final block in the loop, which will start the next iteration. Otherwise, it will continue to the second block. I think I understood this one. So we try to compare the character we enter with the character A, and if it succeeds, then it will move to the next one. Otherwise, it will move to the end of the block. It will start the next iteration. And you see this one. So it moves to the last one, and it go to the it increments the counter, and again it's coming to the next iteration. I'm just clicking this. It goes here and it increments the counter and it compares, and once they incremented the counter register, it's again coming back to this block, the next iteration. And you see the next blocks, it is also similar. It contains the letter Z, and it is actually doing this comparison. It will never occur, so it will just go to this specific condition. So once this condition succeeds, it goes to this one. It increments the counter, and again it goes to the next iteration. All right. And now what happens? What is this RBX? I'm not positive. Let's see. This RBX is actually handling the false condition, I guess. Let me tell you how it is doing that. If the character we entered is not satisfying that condition, it is not in the lowercase alphabet, in that case what happens, this condition, this comparison fails. So it will not choose this condition. Instead, it will choose this red line and it will go to this one. And here the RBX is actually counting the error, right? So whenever we are giving the invalid characters, it's get counted in this RBX register. So that's what we can understand from this. All right. Once again, remember the bigger picture. Okay, fine. Now the part 2. If the second block does almost the same thing as the first one, except it compares the current character with Z. If it's greater than, it will jump to the end. However, there is something very important that easy to skip. Note RBX is incremented, and look at this. The condition RBX is incremented is if the current character is not less than A or not greater than Z. In other words, if it is lowercase character A to Z, RBX is incremented. So RBX is going to be hold the result of how many characters are the lowercase. Okay, I think I was wrong. I was wrong here. Yeah, I was wrong. What happens here? This RBX is holding the correct characters that is getting counted. yeah, that's what happening here. If the comparison uh, fails, then if the comparison passes, it goes to this and it goes to the last block. But I think uh, there is a red line, a red arrow, but it moved to, it is directing to, it's pointing to RBX register, it is incrementing. So what they are trying to say here is, let me read through this once again. The second block does almost the same thing as the first, except it compares the current character against Z. This one. If it is greater than, it will jump to the end. However, there is something very important that is easy to skip. Notice RBX is incremented. This one. The condition in which RBX is incremented is if current character is not less than A and not greater than Z. In other words, if the lowercase a to z, if it is a lowercase a to z, RBX is incremented. All right. So okay, fine. Now what is happening here? This RBX is getting incremented whenever this condition satisfies. The characters are between a to z, lowercase. Then the RBX is getting incremented. So this is actually keeping the counted lowercase values, and this one is actually counting the loops, whatever the string we entered, the number of characters within the string. It could be a uppercase, it could be a lowercase. Whatever the character it is, that's getting counted in RCX. It's counting the loop iteration. It is counting the lowercase letters. So this is very important. Eventually, we are going to print this RBX value only. So let's confirm that. I think this is the block that is printing the RBX, and you see it is printing RBX into, it is actually moving the RBX register value into RDX, and yeah, it's printing that. It's printing RDX. Look at this. All right, I think it makes sense now. The last block, the block that we are currently looking at, it appears it is printing the results out, correct? Towards the bottom of the block, we see something familiar. Comparison of RSI and 0x10. So what is happening? If RSI is less than hex 10, it will jump to the function epilogue. Based on this, we can assume RSI and 10 have something to do with error handling. So this is actually ensures that the program is given a proper input, possibly the input validation or the parameter validation. Looking further, a few small blocks at the end of the function, it seems assumption is correct. Let's get into this. Here, they are actually giving this specific block. It further compares RSI, and we can see the function related to invalid parameters and freeing memory. Let's see. There is a function called JJ free. Might be freeing a memory. Trap debugger. So something related to error handling. Okay. Fine. Remember earlier when I said good reverse engineer note to skip this time, it doesn't. Okay, fine. With this enough practice and experience, okay, these are all the general string, nothing important. Okay, now I think when we started from the first block of this assembly instruction, we tried understanding this assembly instruction better. We had the source code obviously before we start disassembling it. However, we tried understanding what the assembly instruction is actually doing and what register is holding what value. So we tried understanding those stuff, right? Fine. Now let's try to answer this question. In the Loop.exe sample, what instruction is the key to finding out what register is counter? Provide the full instruction with the single spaces. What instruction is the key to finding out what register is the counter? Okay. Now I think they are referring this counter register. Instruction, increment RCX. So whatever the value is entered, so it's gonna it's going to get iterated through the loop, so it is getting counted in this counter register. Fine. Now structures. Now we've done that analysis part. Now we need to check, we need to read through this theory part. Let's see the structures. We will try to finish it earlier. Structures are very common in modern software, especially with Windows. The entire Windows OS is highly object oriented. The general definition of structure is a data type that holds multiple pieces of data. To start, let's look at array, which are essentially the most bare bones data structures you get. All right. Arrays store multiple pieces of data with similar data type. Okay. And you see, let's say we have array of 5 integers, starts with address 4000. The size of the array is 20 bytes. Since each integer is 4 byte, the first integer is something look like this, and the second integer will start from this address. So here they explained the memory address, the structure of the memory, and how it gets addressed when each integer is read or each integer is processed. I think they tried explaining that. And the next one is class. Class have multiple pieces of data and different data types, and you could see this to get a better understanding. This is what makes them harder to work with when reversing. To figure out the layout of the class, you will have to do some analysis. You will need to figure out not only how many things are in the class, but also their data types. There is quite an extensive number of ways to do this, but it generally comes down to just looking at the functions which use the class, paying close attention to, and how they use it. We will take a look at the reverse engineering class structure. Okay, fine. So here is the class structure. Class is human. It's actually a class, and in human, a human has age, height, a name, weight. So these are all the different type of data that belongs to a class human. Okay, and you could see the different data types. Obviously, the age is integer, height is float, and name is a character data type, the string. And the class data type, it will keep 16 bytes, and the 4 bytes for age because it's an integer, and 4 bytes for height, and 8 byte for the name. Pointers hold addresses, and addresses in x64 is 8 bytes. Okay. Now it is actually the pointer to this name, so it holds the address of the name. Since it is an address in 64-bit architecture, it is actually has the size of 8 bytes, which is nothing but 64 bits. How would this be identified in assembly? Well, look at this, how they are trying to represent the same in the assembly. Here they are actually moving the starting address to the RAX register, and then loading the effective address and the next address to enter the age or height maybe. They are just passing that address into RBX register, and the RBX register is containing the address of the height. And the next one, they are adding 8 more bytes, and here you see to RAX. So here when you see, they are referencing RAX every time when they refer a memory location, because this is what they called as offset, and they are referring offset to every memory location. They are incrementing some value with that offset, and they represent they derive the memory location of another object in that way. And the next one is LEA. It is loading the address of the second integer in RCX, and now they are loading the value within RAX and RBX and RCX obviously, and they are loading the name, and you could see the name here. Well, this is how they load different types of data into a register. All right, now it's fine. And now the next one is DLL. It's an interesting stuff. Let's read through this, just a theory. You can just keep it in your mind. Maybe we are going to use these stuffs in our future assessment. Let's see. The process for reverse engineering a DLL is mostly the same as executables, but they are usually easier than you can see in the function name. It's also more common to see debug symbols provided with DLLs that it is to see them with executables. All right, you could see the import and exports and modules. You probably seen many of these function names. Let's see what it is. First, the tool recognizes the function and the names accordingly. So in this para, they explained how a disassembler identifies or parses through the binary that we loaded. It could be a library or an executable. First, the tool recognizes the function and names accordingly. IDA does it with flirt. So this is the engine present in IDA, which is used to identify the function of a binary. Flirt signatures are used to identify standard library functions. The general idea of how they work is search memory of chunk of bytes that match the known chunk of bytes in standard library function, which is actually irrelevant to the context of malware analysis, but to gain an additional knowledge about how a disassembler is working, you can read through this. Okay. And the second, its name may be preserved because it's important from or exported by a DLL. For a developer to use a function from DLL, the developer needs to know to be able to resolve the name of the function they want. Because of this, the names they have to stay intact. DLL can expose its names through DLL-PE header, library files or header files. Fine. What they're trying to say, libraries typically expose their function names. Since the library is gonna get used by various executables simultaneously. Then imports, I already explained this. It contains the list of functions that's gonna get imported from other libraries. All right. Modules are essentially anything related to the process that imports and exports function. For example, Loop.exe includes modules such as NTDLL, kernel32DLL. So these are all the set of DLL files that are getting used by that binary. We can say like that. Modules are list of DLLs used. Okay, name mangling and decoration. C++ function overloading allows you to have two different functions with the same names that take different parameters. This becomes problem when DLL exporting functions, since the exported names will be the same. For developers, this problem is solved using the libraries and header files. On a lower level, the problem is solved by mangling the names so they are all unique. All exported C++ function names gets mangled when they overwrites it. All right. Fine. These are all some advanced stuffs. Okay, let's see running the DLL. When you are up against an exe file, it's pretty simple. It's straightforward. You can load the exe file into your debugger, and you can execute it in a controlled way. But DLL, it's quite challenging because DLL is actually a library file. It's an independent file that is being used by the other programs. It cannot independently run. But to run that, you can use a Windows program called run.dll32.exe. So it's a legit program that is used to execute a DLL file, and you can see the reference here. And there is another, when DLL is loaded, the function DLL main is executed within the context of process, which loads the DLL. Okay, what you can do otherwise, you can load the DLL into another process. In the memory of another process, you can load the DLL and you can execute it in that way. So there are a bunch of other way to execute a DLL. That's the thing. And for reverse engineers, what if you want to dynamically analyze a function within a DLL? The best way to do this is to write your own code which calls the function you are interested, and without a library or header file. And here is a way in which you could call a function with DLL with only .dll file. This will not include or any error handling. So it's only code of interest. It's called the function called add and within the DLL name. Okay, fine. Now this is actually a simple program to load a DLL. We can load our DLL here and we can call it. So this is actually a simple program to load a DLL. All right. So if you want to experiment this, you can just grab this code block from TryHackMe and you can experiment it on your own. Fine. A DLL is an executable on easy mode. All right. Well, let's move on to the conclusion. So the basic hands-on introduction to the, okay, fine. I'll give my own conclusion here. So we have actually tried reversing some basic binaries. Maybe in future we will try to get some advanced binaries. maybe we'll take on some reverse engineering challenges from easy to medium, high level of challenges, and we can try to uh, enhance, upskill our reversing stuff, right? uh, that's one thing. Now I'll close this and let me try opening it with debug symbols and see what happens, because that part that I've never tried. So let me try that. I'm gonna load an assembler, maybe HelloWorld.exe. I'll take load existing overwrite. Okay, and here I'm loading the debug symbols. Let's see. Do you want to browse the PDB file on a disk? Yes, I want to browse it, and here is the PDB file for Hello World, and I'm loading it. And now look at this. What's the difference when it loaded the debug symbol? Anything different? Am I seeing anything different here? They said it's a luxury option to have, but I do not see anything luxurious. Maybe I may not wrong. Maybe I mean I may be wrong. I should be having a better idea about these debug symbols. Local debugger, no debugger. Okay. Quick debug view or a debug window. Start process. Okay. Fine. I think process has exited. So I need to set a breakpoint and I need to proceed. So when we have this debug symbols, I think we can do the debugging stuff. Breakpoints, add breakpoints. Oh, not here. Maybe in the main function. Hello with printf. So here I want to add a breakpoint. So let me add a breakpoint. How I can do that? Debugger, breakpoints, add breakpoints. Yeah, here I'm adding the breakpoint, and in printf I added one breakpoint. I want to remove this. Delete breakpoint. Yeah. So here it is. I'm gonna go and start this process, and now it hits the breakpoint. And look at this. It's stack view, it's hex view, it's the register view. The list of modules got loaded, and you could see kernel 32 DLL, NT DLL. These are all the basic modules to get loaded every time. Threads, you could see HelloWorld.exe. Okay, and I could see the general registers here. Can I see the values present within the register? But here I see the stack view. Maybe we will try to learn all this debugging stuff in our advanced malware analysis room. In TryHackMe, there are rooms that explaining advanced static analysis and advanced dynamic analysis, where we can learn the disassembly and debugging respectively. So maybe we will try to read that. And also the debug symbols, I'm not positive. I'm a noob, I'm a beginner. So I'm not gonna go through that completely now itself. So probably this is the time to end this video. Yeah, I think I took a long time to explain this, though it's a simple stuff. Since I'm a beginner, I took a long time to learn, and I thought to explain this in a clear way. So I tried explaining it as much as possible, as clear as possible. So let's see. I'll try to catch you with another exciting one next time. Until then, I'm signing off. If you like this, if you learned something from this, then consider doing the YouTube algorithms, like, comment, subscribe. I'll catch you next time with another exciting one. Until then, I'm signing off. Cheers, and I love you all. Thank you so much. Bye.